Again, I want to point out the solution is positive Z9 and positive Z16, which again is consistent with the optimization as well as the simulated pupil wavefront errors. For the contact holes on the Mosey mask, I'm showing the experimental best focus as a function of Z9 and the simulated best focus as a function of Z9 for multiple pitches, 90, 100, 110, and 120. Again, the simulation does a good job of predicting the pitch-dependent slope. With only Z9, the delta best focus can only be reduced from 44 nanometers to 27 nanometers. So a similar interpolation was performed in order to find the solution with both primary and secondary spherical aberration. With no applied offsets, the delta best focus through all features were 44 nanometers, and the usable depth of focus was 92 nanometers. With the applied wavefront correction of minus 0.01 and Z16 of minus 0.1, the delta best focus was decreased to 7 nanometers, and the usable depth of focus was increased to 109 nanometers, which is an improvement of 18%. The solution is minus Z9 and minus Z16, which is consistent with the optimization state as well as the predicted pupil wavefront errors found in simulation. An alternating phase shift mask is found by etching into the quartz for every other aperture opening in order to provide an 180 degree phase shift. However, the scattered light from this etched space causes an intensity imbalance, and this results in line pairing. Since less light can get through the etched space prints smaller, so the lines surrounding the etched space are smaller than the lines are closer together than the lines surrounding the non-etched space. And this results in a degraded usable depth of focus between the line space and shifted space. For the line process window is shown in yellow, the shifted space process window is shown in purple, and the unshifted process window is shown in brown. For a pitch of 125, I experimentally showed that the spherical aberration can improve the usable depth of focus. With no applied offsets, the usable depth of focus was 48 nanometers. By applying a primary spherical aberration coefficient of minus 0.09, the usable depth of focus was increased to 97 nanometers. By also incorporating secondary spherical aberration, the usable depth of focus was then increased to 132 nanometers. And now the usable depth of focus is limited by the feature which has the smallest depth of focus, or the unshifted space. For a pitch of 115, similarly, spherical aberration can improve the usable depth of focus. With no applied offsets, the usable depth of focus is 49 nanometers. With the primary spherical aberration coefficient of minus 0.09, the usable depth of focus was increased to 66 nanometers. And by also incorporating secondary spherical aberration, the usable depth of focus did not increase much more, it only went to 68 nanometers, but the focus exposure matrices look much more symmetric. This improvement is not as much as that found from a pitch of 125, and the simulation suggests that higher amounts of spherical aberration could provide a higher usable depth of focus. For a pitch of 150, spherical aberration has been shown to improve the usable depth of focus. For no applied offsets, the usable depth of focus was 0 nanometers. With a Z9 coefficient of minus 0.09, the usable depth of focus was 83 nanometers. And by also incorporating secondary spherical aberration, the usable depth of focus was increased to 141 nanometers. For a pitch of 200, with no applied offsets, the usable depth of focus was 56 nanometers. And with the primary spherical aberration coefficient of minus 0.09, the usable depth of focus was actually degraded to only 31 nanometers. Also incorporating secondary spherical aberration, the usable depth of focus was then increased to 75 nanometers. But note that the best exposure for the shifted space is still much higher than the best exposure for the unshifted space. So this situation would require much higher coefficients of spherical aberration in order to compensate. So this shows that a pitch-dependent trench bias would be required in order to print both a pitch of 200 as well as a pitch of 125. Next, I'm going to move on to the experimental wavefront enhancement with astigmatism. First, I want to show you how a source can shape a line end. the source distribution has a large impact on the image. For example, for line ends where the CD is defined in yellow and the gap is defined in purple, with an illumination of a symmetric C-quad shown here, and the targets are set as drawn on the mask, there is no usable depth of focus between the CD, process window shown in yellow, and the gap for the process window shown in purple. And this is because of line end pullback, where the line prints shorter than what's on the mask. However, with an elliptical C-quad, where the pulls along the y-axis are much larger than the pulls along the x-axis, this elliptical C-quad can stretch the line end geometry and decrease the delta best exposure, reduce the line end pullback, and increase the usable depth of focus between the CD and the gap. Similarly, a pupil can shape a line end. For example, I'm using positive astigmatism in order to increase the usable depth of focus between the CD and the gap, where again the targets are set as drawn. With no astigmatism offset, for a pitch of 100, the usable depth of focus was 41 nanometers. By applying a positive astigmatism offset of 0.05, the usable depth of focus was increased to 135 nanometers, which is an improvement of 229%. Similarly, a coefficient of Z5 equals positive 0.09 was able to increase the CD gap usable depth of focus for pitches of 120, 140, 160, and 180. Now I've reached my conclusions. The mass topography can induce delta best focus, which degrades the usable depth of focus over multiple features. I've experimentally shown that applied spherical aberration can decrease the delta best focus and increase the usable depth of focus. I developed an analytical expression which replicates the experimental trends seen in both pitch and orientation. And this analytical expression can also be used to interpolate for solutions. I found that asymmetric wavefronts can be tuned to particular geometry, such as astigmatism for line ends. And this could be useful in a case which has a mask biasing error, where astigmatism can stretch the image to be closer to what you want. I found a good agreement between the optimized, experimental, and analytical solutions. For the one-dimensional lines and spaces on the Tachyon mask, both the coefficient of Z9 and Z16 were positive. Here I'm showing the solutions from the algorithm in the optimization stage, as well as the analytical expression and the experiment. For the contact holes on the Mosey mask, both the Z9 coefficient and Z16 coefficient were negative. And these signs of solutions have been correlated to the rigorously simulated pupil phase errors. The usable depth of focus improvement was 83% for one-dimensional lines on Tachyon masks, 18% for the contact holes on the Mosey mask, 39% for a pitch of 115 on the alternating phase shift mask, and 175% for a pitch of 125 on the alternating phase shift mask. So this usable depth of focus can bring back advantages of these thicker masks, such as independently tuned phase and transmission, as well as a design or a combination of pitches that previously needed to be avoided can now be used. So in conclusion, pupil wavefront manipulation provides an additional degree of freedom for lithography optimization. Here are the publications that I've had during my graduate career. The top 5 are relevant to my dissertation research, including 2 peer-reviewed journals, one from JM3 and one from Applied Optics. First, I want to acknowledge the IMEC for donating their experimental tools and their materials to me, especially Joost Beckart, Liva von Look, and Vicki Philipson. I also want to acknowledge Kaylee Tencor for the use of ProLith and ProData, and my funding sources, SRC, as well as NSF through the Graduate Research Fellowship Program. I owe a lot of thanks to my committee, especially my advisor, Dr. Bruce Smith, Dr. Roger Zaborski from the Computer Science Department, Dr. Jialin Liu from the Microsystems Department, Dr. Robert Sosha from ASML, and Dr. Grover Schwartzlander from Imaging Science Department. I want to thank the members of my nanolithography research labs, including Neil and Peng, who have already graduated, Andrew, Jermaine, Barack, and Chris, And I also want to owe my family for their moral support, especially my parents, Jim and Leslie, my husband, Tom. Hi, Tom. My wonderful siblings, Wendy and James, who is here, and my best friends, Chelsea and Jamie. Thank you for your time.
Some time for questions?
Correct me if I'm wrong, when you went to a larger contact hole, like 200 nanometer contact hole, you said higher order spherical should help the depth of focus there? Is that what you said?
You're talking about a larger pitch?
Yeah, when you looked at like the 200 nanometer pitch contact hole?
The contact holes that I had 90, 100, 110, 120 nanometer pitches.
What was the last slide that was 200? Was it lines? It could be.
Probably lines and spaces.
Yeah.
200.
So,
You're talking about like one-dimensional lines and spaces,
Yeah.
where the depth of focus was much minimal for like 350.
Yeah.
Mm-hmm.
So were you saying higher order spherical would help there than what you had shown?
Oh, are you talking about the alternating phase shift mask?
Could be.
You must be talking about the alternating
I
phase
didn't
shift
write
mask.
down the slide number. It was just before you switched into the line ends. There.
Yeah, you're talking about the alternating phase shift mask. Okay.
So when you switched, when you went to 200, you had
200. Here.
Mhm.
Okay, so what I mean to say is that for these coefficients, these Z9 coefficients, the usable depth of focus was not optimized completely because see how there's still not a perfect overlap here.
Right.
And I don't mean to say that another higher order like Z36, it's that these coefficients are not large enough.
Okay.
So I need a larger number, like a Z9 of minus 0.15 and a Z16 of 0.2 needs a much higher
Were you
number
limited
in
by
order
the
to
tool?
compensate completely for this pitch.
And were you limited by the flex wave and how far it could go?
Not necessarily. I performed all pitches with one wavefront in order to see if I could optimize for all of them. The flex wave could go larger, but in order to print all pitches at once, I would just use a pitch-dependent bias, and then I would be able to compensate for this. It's just that the optimized wavefront for pitch 125 wasn't the optimized pitch or wavefront for pitch 200 when there's no biasing involved. Same for 115. Because this, they don't completely overlap. So like this, the brown one looks like it could be shifted up a little bit more in order to optimize it. So the coefficients need to be tuned a little bit for this pitch.
Early on, you noted that there was a change in the slope and it occurred somewhere around 100 nanometers. Is that something just a general thing? And if we were to go down to smaller feature sizes, would we expect the trend on to continue?
It's solely based off of the fingerprint of spherical aberration. Because I'm applying Z9, where the Z9,
36.
yeah, well, I guess I can go to near 100 and 110. So the switch occurs right between between a pitch of 100 and 110. So the switch is right here. And it's because of this shape of spherical aberration, this Z9 polynomial. So if I was using a different polynomial like Z16, then the switch would be in a different location because this lobe would be in a different location. So not only does it depend on the shape of the applied aberration that you're using, but also on the illumination. Because for my illumination, where my source pole is at 0.76, which is near the bottom of this lobe, if I had a source pole of, let's say, up here, then the slope switch would occur around pitches that go from the positive to the negative. Does that make sense? So it depends on where you're fitting this quadratic to the 2 points, where the zeroth diffraction order is here and the first diffraction order is here. For this particular polynomial, for a pitch of 100, it results in a positive slope, and for a pitch of 110, it results in a negative slope.
But if you had a higher sigma, to move your zeroth order out radially,
Right, moved it out
you would get what you're calling a switch, actually at,
at a higher pitch.
yes, but actually two switches, because your
Exactly.
radially symmetric position for your first diffraction order would be outside further.
Right, so if my zero diffraction order was here, I'd have a negative slope here for these pitches, a positive slope here for these pitches, and then again, a negative slope here for the smallest pitch over here. So there would be three switches.
Two.
Two switches, three zones, yeah.
So if you're doing a range of feature sizes that were in the 30 to 80 nanometer size, this would be a choice that would factor into how you approach
Yeah,
it.
well, and if you're only on one side of the switch, then they would all have the same slope. But honestly, the fact that there's a slope switch is very convenient because it provides a more degree of freedom in order to find a solution. Because if they all had a positive slope, then it would be harder to find a place where, this one goes up, this one goes down, there's the solution. But if they all went up, then it'd be harder to find that solution. So it's actually very convenient that there is that slope switch.
Yeah, but where your slope is the least is where your illuminator is optimal. It's
And
where
then
your
it's-
zero
then
and first
it's-
diffraction order are symmetrically distributed radially in the pupil. So it's the right solution for sigma center.
For that specific pitch.
Right. It's the main pitch you're designing your illuminator for. Other questions?
So Monica, for your calculation of depth focus in your thesis, you used C4, correct?
You mean when I'm fitting the coefficient for the quadratic? Yeah, I use first order Z4. First order Z4 where I'm just using the slope of a quadratic.
So the focus is proportional to cosine theta.
Right, so I'm only using first order.
And I'm curious because the cosine theta, if you expand that, it has multiple Zernike's, multiple spherical Zernike, Z4, Z9, Z16, Z25. So I'm just curious if there, in some of your best focus that you use, if you use true defocus rather than Z4, would you get a slightly different answer in the sensitivity to Z9 and Z16?
Yeah, I believe you would get a different answer, but based off of how similar my experimental results are to the analytical expression, I think that the difference is going to be negligible because I did get such good matching.
So you're saying that the coefficients, when you expand out the cosine theta are...
The coefficients would be weighted very small, yeah. But I didn't actually perform that calculation.
Okay, any other questions?
Easy one. So how do you change the wavefront in the system?
Experimentally?
Yeah.
So I used FlexWave, which is something that you cannot do here at SMFL. It doesn't have the capability to apply a wavefront solution. So that's why I went all the way over to IMEC in order to use one of their tools. And so they have this really special tool where they have this really unique optical element within their lithography system that basically applies heat in this many different grids, which changes the refractive index at each little location, and then they can create a pattern of any Zernike polynomial. So I guess the answer to your question is by using heat. That's how you change the wavefront.
Do they put that in production tools now?
I don't believe it is in production tools. I know an ASML person would probably be able to answer that better, but I don't believe it's in production, no. I think it's about 4 years old or something like that.
Oh, newer.
Newer than that? Yeah, it was installed at IMEC a month before I used it last March, so, but they were developing it before then, yeah, so it is very new. But very awesome.
All right, anyone else? Let's thank Monica again. So some of us will stick around and Others, grab a snack on your way out this week.